Hi, welcome to Lecture 73, Gravitational Potential Energy. As always with this conceptual physics course, there's no calculus involved. We're moving on past the detailed work on Newton's Principia, but if you're interested in learning more about that, before I get a chance to put up a full lecture series on that, let me just direct your attention to the books by J. Bruce Brackenridge. This is a good book. There's also, you can get the Principia directly in Hawking's On the Shoulders of Giants. There's another book by Nobel laureate Chandra Sekhar called Newton's Principia for the Common Reader. I don't know if it really applies to the common reader or not, but this is also a very good book to review Newton's Principia. But we are going to move on, and today we're going to talk about gravitational potential energy. So recall from lecture 42 that we had said that the force times the displacement, which is of course the work, is equal to the change in kinetic energy. This was the work energy theorem. And further, we said that delta U, the change in the potential energy, is equal to minus the work. Well, this of course applies to conservative work. That's reversible work, as you'll recall, processes that can be reversed. So friction, for example, is not a conservative force, and so the work that's done by friction is not included in the work energy theorem. And so we had done a couple of simple examples. For example, if you think about lifting a barbell over your head in Earth's gravity, right, force, here's x. So if the mass of the barbell is some mass m, that's going to apply a constant force. And if you lift it over some distance delta x, then the work in this case is equal to mg delta x. Probably remember that. So if I lift this pen, from here to here, that's like a quarter of a meter, then I can use the mass of the pen times the acceleration due to gravity at the surface of the Earth, which we'll talk about in more detail later. You can call this the gravitational field if you'd like. Times the displacement will give you the work performed. We also look at more complicated things, so this would be somebody lifting a barbell, for example. What about a spring? We talked about springs as well, right? I should point out before I move on. It's the area under this force versus displacement curve that is the work performed, okay? mg times x, right? That's the work. It's the area under the curve. And so if we look at, say, a spring, which has a force law, which looks like this, minus k delta x. Here's x. Here's F. So if this is our delta x, this point here is just minus k delta x, right? Then we end up getting that the work is equal to minus k delta x squared, right? Because it's, and there's a factor of a half in here, minus 1/2 k delta x squared. Because this is the area under a triangle this time, you see? And so that's half the area of this square, or rectangle that I've drawn here. But what about for Newton's universal gravitation? F is equal to big G, little m, big M, we'll say, over r squared. Well, what does that curve look like? Here's force. Here we'll call this r instead of x. And you can see that as r becomes large, it asymptotically approaches 0. When r is very, very small, it approaches infinity. So what about this law, right? Well, the area under this curve, if we were to say, pick it from some initial r value to some other value, r sub I, let's say, right, it would be the area under here, okay? And that is a bit tricky to estimate, right? Because it's not a simple curve like a rectangle or a triangle, right? So to get the area under here, usually you use calculus. With calculus, it's quite easy. But we don't have calculus at our disposal. So what we're going to do instead is we're going to think about, for this, we'll think of some big mass m that's immovable. It's so large that we'll assume that the remember that there's Newton's third law, which says that for every action there's an equal and opposite reaction, right? So any force that I feel, let's say this smaller mass m over here, right? There's also a force felt on big M, right? It's going to move as well. But if it's really, really big, remember that the ratio of the accelerations is proportional to the ratio, or the inverse ratio of the masses. And so for a very large, massive object, it's not going to move very much, right?
Yeah.
So we can assume that that's stationary, okay? If the mass is very large. And so here, the distance from the center of, say this is the sun or something, this might be Earth, right? This distance here is what we'll call r. And we're going to consider moving it a little distance farther away like this, okay? So, and we'll call this distance r sub I. Okay? So we're going to move it just a little bit away. We can write that the work for this little displacement that I've done here is going to be, I'm going to call big G, so we'll let K be equal to big G, big M, little m. Right? This top part's all I'm left with is the 1 over r squared part in the force law, right? It's going to be equal to K times 1 over, and what I'm going to do is I'm going to use the average value, okay? Instead of using Ri and R directly, I'm going to use the average value to calculate what that force is at this point, okay?
Okay.
So it's the average value between here and here. So it's going to be 1 over Ri plus R divided by 2, all of that squared, okay? So this is called the arithmetic mean. You probably know it as just average, but average is what we refer to as the arithmetic mean. You take two things, like say R and Ri, you add those two values together, you divide by 2. Why 2? Because you added two things together. If I add three things together, I divide by 3, right?
Yeah.
It's just like the same thing you'd use in like a class average. You add everybody's test scores up, however many test scores there were, or how many tests there were, you divide by that number, right?
Yeah.
So it's called the arithmetic mean. But it's not the only kind of mean that's out there. There's another mean called the geometric mean. And that I'm going to have to digress just a little bit, so we'll have a little mathematical digression on the arithmetic mean, because we're going to use that. Okay, so I've drawn a little figure on the board here, with points P, Q, and R, and also the point A, and the point O, point A, and the point G. So what is this that I've drawn? Well, let's let A be equal to this line P, Q. Really, it's the distance, right? It's the distance from P to Q. I'm going to let B be equal to the distance from Q to R. Now, by definition, this point O is at the center of P and R, right? So this is the arithmetic mean. So we would write AO, and what I've done is I've then used this distance AO to construct a circle, right? Going between all these points here. So it's just, or a semicircle, I guess it is. So AO, which is the, I'm just going to call it the, well, I need to write arithmetic mean. AO is equal to A plus B divided by 2. So it's this length plus this length divided by 2, okay? Because the distance from P to Q, that's A. The distance from Q to R, that's B. I add those two together, divide by 2. It's plopped down right here in the middle, right?
Yeah.
I then extend this arm upward and swing it around like to create a semicircle. You see how I did that?
Yeah.
So at this point A here, AO, is equal to PO, which is equal to OR, right? And that is equal to the arithmetic mean, okay?
Okay.
Now, I can draw a line from P to this point G. So what I do now is I take the point Q, which marks the left-hand side of this length B, right? Going from Q to R, right? And I just create a perpendicular by construction, right? So this is perpendicular to the line PR, and take it up here to this point where it hits the semicircle circumference, okay?
Okay.
Now, you may be familiar with Taylor's theorem regarding right triangles. You can inscribe a right triangle inside of a circle, exactly as drawn here, right? So that means that this angle is right, okay, which makes this a right triangle. If I label this distance from Q to G, and we'll call it H for height or altitude, that's the altitude of this triangle, right?
Yeah.
So let's write H equals QG, okay?
All right.
I'm going to label PG X. So we'll call this X, and I'm going to label RG as Y, okay?
All right.
So RG is Y, So why have I done that? Well, because I've got three triangles here, right? I've got the big triangle, which is a right triangle, right?
Yeah.
And that will have the relationship that x squared plus, let me put y here, plus y squared is equal to this distance from P to R squared, which is just a plus b squared, okay? So we can write x squared plus y squared equals a plus b quantity squared, okay? But I also have this little triangle, we'll call it 1, right? It goes from P, G, Q, right? You see the triangle? So we'll say that triangle 1 is equal to, we'll call it triangle P, G, Q, okay? And so triangle 1 has the relationship that, what is this distance PQ? Well, that's just A, right? So it's got A squared plus this distance QG is H, that's H squared, is equal to this distance X squared. Okay?
Okay.
Because this is a right triangle by construction, so this X is the hypotenuse of it, right?
Yeah.
Similarly, we have this smaller triangle, 2, over here, which we'll define as 2 is equal to this triangle, we'll call it RQG. 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 It's this triangle right here, right? It's also a right triangle by construction, which means that this distance QR, which we call B, B squared, plus H squared, is equal to Y squared. Okay?
All right.
So I'm just writing Pythagorean's theorem for three triangles. The big triangle, which is right by Cayley's theorem, okay?
Okay.
Since it's inscribed inside the semicircle. The little triangle 1, which is right by construction, okay? Because I basically, from point G, I dropped a perpendicular, right? And this other triangle 2, which is also right by construction, okay? If I add these two together, let's add these up, right? We'll get A squared plus B squared, right? Plus, that's 2H squared, right? Is equal to X squared plus Y squared. Yes?
Yeah.
Well, X squared plus Y squared we have from this relationship here, right? That's just equal to A plus B squared, okay?
Okay.
So if I set the left-hand side equal to the right-hand side here, I'll get A squared plus B squared plus 2H squared equals, I have to square this out, right? So that's A squared plus B squared plus 2AB, right?
Yeah.
The A squareds cancel, the B squareds cancel, and I'm left with 2H squared equals 2AB. Divide out the 2, take a square root. We get that H is equal to the square root of, not 2, the square root of A times B. H is known as the geometric mean, okay?
Okay.
It's not as common as the arithmetic mean. I encourage you to look it up online. You can probably find many nice details about the geometric mean and where it's useful. But we're going to use it here. Now, what do we want to say about it? Why is it useful to us? Well, because notice that there's a relationship between the arithmetic mean and the geometric mean, right? This line AO, or OA, right, is the arithmetic mean. H is the geometric mean. If I allow the difference between A and B to be very small, that means they're very close to the same size, right? So imagine moving the point Q closer to O, okay?
Okay.
So that these two lengths that we're averaging together arithmetically are about the same, right?
Yeah.
If that's the case, then that says that the arithmetic mean is approximately equal to the geometric mean, okay? So the relationship that you can see here is that A plus B over 2 is always greater than or equal to the square root of AB, okay? You see that? Here's H, or square root of AB.
Yeah.
OA, which is the arithmetic mean, will always be greater than or equal to QG, right? If I let Q move closer to R, right, this gets smaller, right?
Yeah.
If I let it get closer to, let Q get closer to O, then they become approximately the same, okay? So for a very small difference between these distances, A and B, right, the arithmetic mean is approximately the same as the geometric mean, okay?
Okay.
So we're going to use that in our work from before. Okay, so I put our gravitational problem back up on the board again with our very large mass M and its gravitational effect on this smaller mass little m, which is separated by some distance r, and we're going to imagine performing work and moving it from r to r sub I, some little distance away, okay?
Okay.
And to map it back onto the arithmetic and the geometrical mean from before, r sub I plus r over 2, which is the arithmetic mean, right, so somewhere here, is greater than or equal to the square root of ri times r. Okay? That's the geometric mean. Okay?
Okay.
Now, if delta r, which is defined as ri minus r, is small, then ri plus r over 2, the arithmetic mean, is approximately equal to the square root of ri, r. That's what we showed just a moment ago. Okay?
Okay.
So we're going to use that here. So we'll write that the work is approximately k times 1 over ri times r. Why ri times r? Because we square the arithmetic mean. This is supposed to have a divided by 2. Sorry. And that should all be squared. There we go. Okay?
Okay.
So I'm just replacing ri plus r over 2 with the square root of ri times r, which when we square it, we get this. K times 1 over ri r. Okay?
Okay.
So let's do this one step at a time, right? So why did I use ri, or r sub I? Because I'm going to imagine moving it out, doing work in little tiny increments. First I'm going to move it a little bit, take a little step, and then I'm going to take another little step, then I'm going to take another little step, and then I'll add up all those little steps to get the work, okay?
Okay.
So let's do it one step at a time. So let's call the first step would be equal to k. And let me just, before I do that, I'm missing, missing an important thing here. We have to the work is the force times the displacement, so it's times ri minus r, okay?
Okay.
And so this would also be times ri minus r. I hope I didn't leave that out before, but because it's force times displacement, right? And so the displacement is the difference between ri and r. It's this little bit of distance that we moved it, right? Okay, well, it's in now, okay? So when we put that in, right, we can rewrite, before I do this, let me just show that the work in this case we're going to say is equal to k. And I'm going to divide through by ri over r, right? If I multiply it using the distributive property on ri minus r, I get k times 1 over, well, ri over ri over r will just be 1 over r, minus r over ri r will be 1 over ri. Okay?
Yeah.
That's just the distributive property, okay? Now we're going to take these little steps one at a time. So the first step will look like k times 1 over r minus 1 over what we'll call r sub 1, okay? Step 2 will look like k times 1 over r1, that's where we're starting, minus 1 over r2, the next place we're going. So that's going out a little bit farther, right?
Yeah.
W sub 3 will be k times 1 over r2, which is where we start, minus 1 over r3, which is where we finish. And we can keep going like this. We'll get, for the n minus 1 step, it's k, 1 over r n minus 2, the previous step, minus 1 over r n minus 1, which is where we're at now. And then finally, if you go all the way out to the nth step, or the final step, it's equal to k times 1 over r n minus 1, or r sub n minus 1, minus 1 over r n. Okay?
All right.
And here's what to notice, right? Remember, we have to add up all these little steps together to get the work, right? The work is going to be equal to the sum over all of these steps, right? We'll call it the r sub I, where I goes from 1 to n, okay?
Yeah.
We have to add all these little pieces up. Look what happens when we add them, though, right? When I add, say, the first step to the second step, look what happens. We have a minus 1 over r1 term here and a positive 1 over r1 term here, you see?
Yeah.
Those will cancel. And you can see that in the next step, the r2 will cancel with the minus 1 over r2 in this step. You see that?
Yeah.
And the same thing happens across the board until you get to the final step, right? And so what you end up getting is that the work is equal to k, because k is always there, times 1 over r, which is where we started, minus 1 over r n, r sub n, which is where we end up, okay?
All right.
Now here's what we're going to do. We're going to take the limit, right? We're going to let the final step be all the way out at infinity, okay? And this is a typical thing that people do with gravitational potential energy, right? They let kind of the default position that you go to be infinity. So you imagine, typically they would say, oh, we're going to bring it in from infinity and see how much work is done. Here we're kind of doing it backwards. We're saying we're going to start from some known distance, r, and we're going to move it out to infinity and see what the work is, okay?
All right.
What I'm really interested in, I know this is technically from calculus, limits, right? But we're going to look at the limit as n approaches infinity, okay?
All right.
Or really, it's r sub n approaches infinity, okay? Of the work, which is, of course, k times 1 over r minus 1 over r to the n, r sub n, okay?
Okay.
Well, as r sub n goes to infinity, right, nothing happens to this first term, right?
Yeah.
But this second term, we have 1 over infinity. What is 1 over infinity?
Z-
You
Zero.
almost said yes, that's right, 0, right? So this is equal to k times 1 over r. Okay?
Okay.
And so the potential energy, which is equal to minus the work for gravity, I'm going to put k back in again, okay? Remember k was equal to big G, big M, little m, equal to minus big G, big M, little m over r. Okay?
Okay.
Okay, and so this result that we get, that the potential energy, or the gravitational potential energy, is equal to minus big G mm over r, is the same result we would have gotten if we had used calculus to get the gravitational potential energy. Okay?
Okay.
And we'll use this in the next lesson. I think we'll use it in the next lesson. Yes, we'll use it in the next lesson to try to understand orbits and things like that using gravitational potential energy. Okay?
Okay.
But we have to get this result first. So it differs from the force law, right? We write the force law right next to it, right? The force is equal to big G, big M, little m. Or actually, let me write it like this. Let me write it more generally and say that delta U is equal to minus G M1, M2 over R, and that the force is big G M1, M2 over R squared. Okay?
All right.
So here, M1 is just our big M, right? M2 is our little m, but this is for any two masses that you might consider, okay?
Okay.
These considerations are always between pairs, okay? Maybe we'll talk later about what if you have 3 or 4 or 5 masses interacting with each other, okay?
Okay.
But we actually won't do a whole lot of stuff there. That's going to be tedious, and it's the kind of stuff that you deal with in a more calculus-based approach course, okay? But yeah, this is our final result, that for Newton's gravitational force law, the potential energy that results is minus G M1, M2 over R. That's it.